Okay, so our speaker today is Ben Steinberg, and the title of his talk you can see there is Simplicity of Nekrashevych Algebras of Contracting Self-Similar Groups. Please, Ben, go ahead.
Okay, thank you for inviting me and giving me the chance to speak here. This is joint work with Nora Szakacs, who's now at the University of Manchester. It's been around a while, this result, but I don't think I've spoken about it at a place where maybe most of this audience would be, so far as I know, but maybe somebody's already heard this talk, in which case or some version of this talk, in which case I do apologize. But okay, so that's my outline of my talk. So I'll start off by reminding you what are self-similar groups, or maybe tell you for the first time. Then I'll talk about what are Nekrashevych algebras, and then if time permits, which will hopefully it won't, but if it does, then I'll say something about techniques. For these self-similar groups, I'm just dealing with the very classical case of self-similar groups. People have generalized these, like Quiaxel and Enrique Pardo have generalized this beyond just the classical case of acting on alphabets, but I'm going to stick to the classical case here. I mean, I think many of the things will generalize, but we just didn't focus on that. So I'm going to assume that X is always a finite alphabet, which just means a finite set with at least two elements. And then we have the Cayley graph of so X star will denote the free monoid on X. So it's just the monoid of all words, including an empty word. And the Cayley graph of this is just a regular rooted tree. So for instance, if my alphabet just consists of 0, 1, then the Cayley graph is this regular rooted binary tree. You can see I labeled the vertices by the words. I didn't label the edges because you can figure them out by looking at the vertices. And this is what it would look like. And these slides were probably made long ago when the audience was more geometric group theory and they like these pictures. And then we can look at the boundary of this tree. That's just all the infinite rays starting from the root. And this looks just like an infinite path is basically the same thing as an infinite word, right? So if you have an infinite word, there's a unique path that it labels. And so you can identify the boundary of this tree with the infinite words with the usual kind of cylinder set topology. So it's a Cantor space. And the automorphism group of this tree acts on this Cantor space by the natural way that the automorphism of a group acts on fixing the root, will act on the space of infinite paths starting at the root. Notice that any automorphism of this tree preserves the root because every vertex has degree 3 except the root. The root's unique vertex of degree 2, so any automorphism must fix it. And therefore it preserves the distance from the root. So it preserves word length if you like. Okay, that's what this is saying. So because it preserves, maybe I'll go back to the picture a second. Because the root is preserved, the action of an automorphism must shuffle around these two trees, the tree of things starting with 0 and the tree of things starting with 1. So I call Tx the tree of things starting with X. So the vertex set are all words starting with X, and these trees will be permuted around. And if GT takes Tx to Ty, then after all these trees look exactly the same. I'll go back. This tree looks exactly like the full tree by just removing the first letter. And this tree looks exactly like the full tree by removing the first letter 1. And so if I do this identification, then the action which takes of G taking the X tree to the Y tree can be viewed as given by an automorphism from the original tree after we've done these identifications. So algebraically, what this means is if I have a word XW starting with the letter X, acting by G, I basically do whatever I do to X, and then I do this thing here, which is called the section, to what remains of the word. And we call this guy the section, or sometimes it's called the restriction. One of the things about self-similar groups is Nekrashevych very often changes the terminology from paper to paper and book to book. So sometimes it's easy to get out of date. Maybe I'm out of date on this now. And more generally, you can define sections at any word so that you have the same rule, that if you have this word u times some element, you just apply g, the permutation to u, and then you do the section at u to what remains. So you can think of this as you look at the subtree hanging down from the vertex labeled u, and you move that to some other tree that looks up to isomorphism in a canonical way like it, and you apply this permutation GU. And this is the formula for how you get the iterated sections. If you have a word x1 through xn, where those are the letters, then the iterated sections, you take the section of G at the first letter, and take that guy's section at the second letter, and so on and so forth. And this subgroup of T of x is self-similar if it's closed undertaking sections. So what this means is when you act, so maybe I'll go back to the picture. So our element of our group might take this tree to that tree. But if we don't put any restrictions, what the isomorphism between this subtree and that subtree under our canonical identifications might not belong to our group G. And the group is self-similar if all the actions you see on these subtrees are given by elements of the group. You know, once we've done our canonical identification, that we can identify any subtree with the whole tree by just removing initial letters. And so that's what this self-similar group is. It's closed undertaking sections. So in particular, the whole automorphism group is self-similar. There are some very famous examples of self-similar groups, like the Grigorchuk 2 group, the Sidkey P groups. Grigorchuk and Zook used a self-similar representation of the lamplighter group in the early 2000s to disprove the strong form of Atiyah's conjecture on L2 Betty numbers. Now much more was done, but that was kind of the starting point. Bartoldi and Nekrashevych used self-similar groups called iterated monodromy groups to solve Hubbard's twisted rabbit problem in complex dynamics. And okay, so this is sort of why they're kind of interesting. A lot of interesting problems have been solved. This is by no means a complete list of interesting problems which have been solved using self-similar groups. And any self-similar subgroup of this automorphism group acts on infinite words. So for those who are familiar with self-similar groups, what I'm really talking about are sort of faithful self-similar group actions, which is initially what people talked about. But eventually Nekrashevych said, we don't really need, we can talk about self-similar actions that are not necessarily faithful. And those are also useful, but in this talk, I'm only doing faithful actions. All right, so next I'm going to talk about automata, because automata is really where the theory of self-similar groups began. The theory of self-similar groups began with people like Alyoshin and Glushkin in the Ukraine in the 70s, who were studying automata theory in computer science. So I'm going to give a convenient definition of an automaton for this talk. It is not the definition you would find in the computer science book, and it's only actually a special case, but it's the case of interest. So for us, an automaton is going to just be a finite set of automorphisms of this tree, which is closed under taking sections. But it's not necessarily a group. It's not closed under products. And we give them by or represent them by what are called state diagrams. So the vertices of this state diagram are just the elements of this automaton. So it's a finite collection of tree automorphisms. And the edge from an automorphism A has a label. On the left side, the label is going to be an element of the alphabet, which is an input X. And the right side of this label is what this permutation does to the letter X. It's the output. So the input is X, the output is A of X. And then when you read X, the next thing it will do is move to a new state, which is the section of A at X. I'll have a picture up in a second so you can see how it goes. And if you take a subgroup generated by an automaton, it turns out to always be self-similar. And it's kind of the easiest way to specify a self-similar group. And such groups are called automaton groups. And they were studied long before self-similar groups were defined in general. And automaton groups have the nice property that they always have a decidable word problem. You can use basic computer science to solve the word problem. The word problem can be solved in polynomial space, which is not the same thing as polynomial time. Polynomial space to simulate in time it usually takes exponential space, unless some weird hypotheses of computer science break down. And there are examples of automaton groups with a p-space complete word problem, which means that you can't do better than this p-space algorithm. So let me give you an example of an automaton. So this is an automaton doing what's called the adding machine. So this automaton has two states, A and B. So these represent two automorphisms of the binary tree. Oops. So on state A, if your input is 1, you output a 0, and you return to state A. And if you're at state A and your input's a 0, you output a 1, and you move to state B. If you're in state B, if your input's a 0, you output a 0. And if your input's a 1, you output a 1, and you always stay at state B. So what this means is that the section of A at 0 is a B, because when you see a 0, you move to B. If the section at 1 is a A, because if you see a 1, you stay at A. And if A sees a 0, it outputs a 1. And if it sees a 1, it outputs a 0. And B will output whatever the input is. It doesn't change the input. And so just to do a sample computation, you can see how to compute words right off of this. If you in blue, you'll see the current input and output. So the input is a 1, it will output a 0. And then it will move to state A. And at state A, it sees a 1, so it will output a 0. And now it will move to state B, where it's, still at state A. Now it sees a 0, so it's going to output a 1 and move to state B. Now it's at state B, it sees a 1 and it outputs a 1. And so that's the output of that word. So that's how these machines work. And so this graph encodes how the automorphism works. And for me, that's the easiest way to understand how the automorphism works. B just computes the identity function, because you always, given any input, you output the same letter, and you never leave state B. So you're just going to keep outputting whatever you input. And so these guys generate a copy of Z. And if you've used infinite strings of zeros and ones as two-adic numbers with least significant digit first, then this is adding 1. So it's sometimes called the two-odometer. So the earlier work of Grigorchuk and later group Desitki was very much based on the property of their groups being contracting, which was kind of defined in a somewhat informal way. So roughly speaking, an automaton group is contracting if there's some constant smaller than 1, so that whenever you take the word length, L means word length. So these groups are finitely generated. Your automaton has finitely many states, and so you can talk about word length. And it should be that the word length of the sections contracts strictly from the word length of the full element for large enough, for elements of large enough word length. So very small word length things do not have to contract. But from sufficiently long words should contract. And this lets you kind of do induction. And so like the way Grigorchuk proves that his group is an infinite 2 group is he does induction on the word length, and then he uses this contraction property to eventually get that the sections you all see have finite order. Now you have to do a little bit of a trick to also make sure you have to actually raise it to a power first and still have things contracting. But anyway, that's the idea. So Nekrashevych formalized this notion of contraction in a way that makes sense for any self-similar group, even ones which are not finitely generated, and therefore it doesn't make sense to talk about the word length.
So sorry, the word length. I mean, when the group is generated by an automata, you use
the generators of the states. Yeah, the states of the automaton are the generators, and so you have a natural word length. Because the automaton's finite. Yeah. So Nekrashevych, but you can have infinite self-similar groups, and you can have infinite ones which are contracting. And so Nekrashevych formalized contracting in a way that doesn't talk about word length. So he calls self-similar group contracting if we can find a finite automaton contained in G. So that just means a finite subset of G closed under sections, with the property that given any element of G, there's some number K, so that any section of G along a word of length K. So X to the K is the set of words of length K. So there's some, if you go on sufficiently long words, the section of G belongs to the nucleus. Once a section belongs to the nucleus, since the nucleus is closed under sections, it remains. All further sections are also in the nucleus. So what it says is from some point on, for each element of the group, from some point on, it only acts by elements of the nucleus. like far down the tree. So this relates to the old notion, and there's a smaller such n, which is called the nucleus. So I guess it's probably said a little bit later in the slide, but the idea is if you have this contracting property based on your word length, each time you take a section, the word length contracts. So if you take enough sections, your word length will get smashed down to things whose lengths are too small that they may not contract anymore, and that will kind of be how to get your nucleus. In any event, Volodya has in his book algorithms to decide if an automaton is a nucleus, and there's kind of a partial algorithm which, if you have an automaton, will try to find the nucleus, and if your group is contracting, it will eventually find the nucleus, and if your group is not contracting, then it will not halt. And if you go by the classical approach, then the nucleus consists basically of those elements whose sections don't contract, or at least it's a subset of those elements whose sections don't contract by the factor lambda. So the idea, if you're given any element, by iterating sections, long enough sections, the length contracts below the point which you no longer have the contraction property holding, and then you're within some finite set of elements of a particular word length. And so important examples include Grigorchuk's group Desiccii groups, GGS groups, which stands for Grigorchuk group Desiccii groups, something called Synic groups, which I'll talk about later, something called spinal groups, which I won't talk about, the Basilica group, which I won't talk about either, the Hanoi Towers group on 3 pegs, which I also won't talk about. But anyway, it's a significant class. A lot of iterated monodromy groups of certain kinds of post-critically finite rational functions are contracting. So contracting is one of the most studied classes of automaton groups. Okay, so before I move into algebras, any questions about self-similar groups? I know if you've never seen it before, it's kind of a lot to absorb.
Yeah, well, I should say that I have read Excel Pardo's paper and thought about, and based on that I wrote a paper on Excel Pardo algebras and so on. But until recently, preparing for your talk, that I went to read Nekrashevych's book, I hadn't made a connection that this one cocycle presentation that it meant this. I mean,
yeah, so that's what the one cocycle means. It means this restriction property. I mean, Nekrashevych in his book does things in terms of these bimodules, and the one cocycle is sort of how to express the bimodule once you've chosen a basis. There are several different ways to express it. In the old language, people use the one cocycle to talk about Reith product embeddings. So there's a lot of different languages for this. But yeah, so this was a very classical language. Excel Pardo approach takes a different language. But these are equivalent languages. You can sort of talk about their language also in terms of these types of things. So let me now tell you about the algebras. So Nekrashevych introduced C-star algebras associated to self-similar groups, which generalize Kuhn's C-star algebras. And then he later considered analogs with coefficients in the field and used them to construct interesting examples of algebras, including he disproved the conjecture of Jason Bell on whether there are about simple algebras in characteristic 2 with Gelfand-Krylov dimension, I forget, certain 2 or something like that. Okay, and the C-star algebra is the completion of the complex Nekrashevych algebra with respect to an appropriate, C-star, pre-C-star norm. And these things generalize the classical Levitt algebra L1n. Or LN1, I'm not sure which order you put these in. And they've been studied by a number of people, including Clark, Excel, Pardo, Sims, Starling, Norenai, and others. So let me tell you how I think about the Levitt path algebras on the loop. That's basically what I'm talking about. So we could take a vector space whose bases are all infinite words. And then for each letter, you have an operator, which I think of as pushing the letter X on the top of a word. So you can think of an infinite word as like an infinite stack if you're a computer scientist. And then one thing you do with a stack is you push a letter on the top. And then there's sort of an adjoint operator, which computer scientists would call popping a letter, which says if the top letter is X, we pop it. And if it's not X, well, we don't know what to do, so we say 0. And in fact, this Leavitt algebras were also rediscovered by computer scientists who were trying to model exactly this stacks. So this concept, this kind of algebras have been rediscovered many times by different groups of people. And if you stare at these operators, they satisfy some obvious relations. Like if I try to push on a letter X and pop on a different letter Y, I will get 0. While if I pop up the same letter, I will not have done anything. And it also satisfies the fact that if I try that this operator is 1, this operator basically finds the first letter, removes it, and then puts it back on. And the algebra defined by these relations is called the Leavitt algebra L1 size of X. And it's a finally presented simple K algebra acting faithfully on this set. And its unit group contains some interesting groups like Thompson's simple group B, which, at the time when this was first discovered independently by Nekrashevych and Berger was like a big deal. Now we all understand sort of why this is the case. Okay, so now we have that our self-similar group also acts on the vector space with basis the infinite words, because the group acts, any automorphism of the tree acts on infinite words by just continuity basically. And so therefore it acts on this vector space. And so it's natural to look at the algebra generated by the self-similar group and this Leavitt algebra. And this is similar for people who do group theory to the way Rover, notice that Grigorchuk's group and V are both acting on this infinite alphabet, so he generated something by the two of them, which turns out to be the full group associated to the groupoid associated to the Grigorchuk group. So in addition to the Leavitt relations and the multiplication table of G, which are obviously satisfied by these operators, there are some other relations which reflect the self-similarity structure. Namely, if I first act by putting X at the beginning and then do G, that's the same thing as acting by the section of G of X and then doing G of X. Just because that's how you act on a word, right? G of X times W would be G of X, G section X on what, on W. And then there's a dual version of this because I'm doing this as a ring instead of a star algebra. But let's ignore that. So the Nekrashevych algebra is just the K algebra generated by G. The X is the X star subject to the Leavitt algebra relations, the multiplication table of G, and the above relations. If you write it as star algebra, then you can forget about 2 and just do 1. I don't know, when I wrote the slides, I didn't want to do star algebras, but ask me why. And it turns out that if you look at the K algebra generated by the Leavitt algebra and G acting on this, it's the unique simple quotient of the Nekrashevych algebra. It's not in general the Nekrashevych algebra, but it's the unique simple quotient. It can have a kernel. So this algebra is simple precisely when this representation on infinite words is faithful. And Nora and I, some ongoing work with Chris Bruce, have some sort of more general discussion of what the relation is. So this quotient is what's called the essential algebra these days, and we have a similar kind of representation, which for appropriate kinds of groupoids, which tell you what the essential algebra looks like, but it's not fully written up. I don't know where to start.
Sorry, since you before said that I had misunderstood that you had put CK2 among the relations in the previous slide. You didn't.
When I said the Leavitt relations, I meant including CK2.
Okay, so wait. Okay. So
but because of the group being thrown in, you can lose simplicity.
Okay.
So the Leavitt algebra still acts faithfully on in this representation, but the subgroup elements may not act the way they're supposed to.
Okay.
We'll see an example in a moment where of group elements not doing what they're supposed to do. Okay, so this algebra is simple precisely when this natural representation is faithful. And you need the complex algebra to be simple for the C-star algebra to have any hope to be simple. And these algebras are étale groupoid algebras for an appropriate groupoid. And the corresponding rings are étale groupoid algebras for the same groupoid. And these groupoids satisfy all the conditions for a Hausdorff groupoid to have a simple algebra. But these groupoids are not usually Hausdorff, these Nekrashevych groupoids. I mean, we know what the condition is, and it's just not usually satisfied. So, for instance, in 2015, Nekrashevych observed in his paper that the Grigorchuk group does not have a simple algebra characteristic 2. The Grigorchuk group acts over a 2-element alphabet, and it contains a Klein 4 group on elements B, C, D, and E, which fix the infinite path 1, 1, 1, 1, 1, 1. And on any other infinite word, exactly 2 of these elements agree. So 2 of them will do one thing and the other 2 will do something else. And so if you add all 4 of these guys, they're going to, in characteristic 2, they annihilate any infinite word. Either you'll get, on 1, 1, 1, 1, 1, you'll just get 4 times that 1, 1, 1, 1, 1, 1, 1. And on any other infinite word, you're going to get 2 times whatever 2 of these guys do plus 2 times whatever the other 2 do. But you can show that this element is not 0 in the Nekrashevych algebra. And so this is something in the kernel of that representation, which is non-trivial in the original Nekrashevych algebra. So, and Clark, Axel, Pardo, Sims, and Starling, in a paper that came out in 2018, proved that the algebra of the Grigorchuk group is simple over fields of characteristic different than 2. They also rediscovered that it was not simple in 2. I think when they wrote the paper, they didn't know about Nekrashevich's paper. But they proved, and they also showed that the C-star algebra is simple. Well, that's what the next line says. Nekrashevych published in an email to Enrique and other authors on the Clark, Axel, Pardo, Sims paper, showed that the algebra was called the Grigorchuk-Oechsler group, which is a group introduced by Grigorchuk and studied by Oechsler, and that looks on the surface similar to the Grigorchuk group, but it's a bit different. Had a simple algebra over no fields whatsoever. Nora and I also rediscovered that, but then Enrique informed us of Nekrashevich's email. Or Nora rediscovered it. I had nothing to do with it. Okay, for contracting groups, the C-star algebras and the rings are finitely presented. This was shown by Nekrashevych in his paper. The algebra is just generated by the letters and the nucleus. And the relations are those the Kutz-Krieger style relations and the relations from the Nekrashevych algebra that involve nucleus elements. So you need things like if the product of 2 nucleus elements is a nucleus element, then you have to put that in, and then the relations involving sections, but only for nucleus elements. So it becomes a finite presentation. You don't throw in the whole group multiplication table, only the ones involving nucleus elements whose product happens to be a nucleus element. In particular, the algebra depends only on the nucleus and not on the group. You can have multiple groups with the same nucleus. I mean, in most interesting situations, the group is generated by the nucleus. And this is basically saying, from the point of view of the C-star algebra, you might as well see that. Okay, so first result that I guess I'll state by us is that if you have a contracting group over the alphabet A, then either the Nekrashevych algebra is simple for no field whatsoever, or it's simple for all fields except those of finitely many positive characteristics. So as soon as it's simple over any field of positive characteristic, it's going to be simple over the complex numbers or any field of characteristic 0. The simplicity of groupoid algebras, of ample groupoid algebras, depends only on the characteristic, not the field. It's just a characteristic issue. In general, for groupoid algebras, this word finite is not required. This is special to Nekrashevych algebras. For general groupoid algebras, if it's simple and positive characteristic, it must be simple and characteristic 0. But you could have kind of any behavior you like as to which positive characteristic is simple. Well, here, if it's simple for any positive characteristic, it's simple for all but finitely many. You can only have finitely many bad cases.
But these are groupoid algebras, or aren't they?
Yes, but they're special.
Okay.
They're better behaved than the typical case. So we have examples over infinite alphabets where this kind of behavior disappears. Also, we show there's an algorithm which, on input the nucleus of the self-similar group, will output the set of characteristics for which the field is not simple, or tell you that it's never simple. So, I mean, many self-similar groups are given by their nucleus, and if it's not big, you can try to plug it into the algorithm and get an answer. We did it by hand for some small examples of well-known self-similar groups. Abstractly speaking, the algorithm doesn't look like it has to give an answer that quickly, but we've never ran into an example where it doesn't come out quickly. So either we're not very creative, or maybe the algorithm somehow is more efficient, and some of the things that we say to do never really need to be done.
But
I don't know what the
do you have an
algorithm
estimation of how long it takes? Like in
there's some sort of exponential upper bound, but it doesn't seem to ever happen. So at a certain point, you have to build a certain finite state automaton, and the upper bound we have is on how big that automaton can be is exponential. But in no example have we ever constructed does it ever even get close to that. So it would seem to suggest, experimentally, that one should be able to prove that you only need certain of these states and not as many as we say you might need. So in practice, it never seems to get as big as it could in theory, but we don't have a theoretical bound on it.
So maybe a probabilistic approach.
Yeah. So I don't know. I don't have any real. Yes, we didn't think that hard on trying to improve the time complexity issue. We know where the hurdle is. If someone can show that this particular automaton we construct has a much better bound than what we give in size, then the rest of the algorithm is efficient. It's just that one part. So there's sort of a theoretical description which underlies the algorithmic result. And this theoretical thing is often usable in practice. So like if you hand me an infinite family of examples, like unique groups, then we can tell you what the answer is. Obviously, you can't run an algorithm on an infinite family of examples, right? But we also understand what's going on. The algorithm is one thing, but we actually have a theoretical description that we can use to actually prove results. We also construct for any finite set of primes a contracting group which is simple precisely over those fields whose characteristic does not belong to that finite set. So in other words, this thing in part 2 that is simple for all but finitely many sets of primes is the best you can say. You can always, given any finite set of primes, we can give you an example where that's the set that comes up. So there's no further relationship between primes other than this. So as an example, I'm going to talk about Sunik groups because I can state this one concretely without going through a lot of crazy definitions. So let's take a prime P. So first of all, sorry, because this is supposed to be Z mod P, not the p-adic numbers, okay? This is integers mod P. I'm sorry. Maybe I should have written FP. So I apologize to all the number theory people out there who use p-adic numbers. But what does contracting mean here? Contracting is this property that any element of your group, from some point on, its sections belong to some finite set that's independent of your group element. There's one finite set which is closed under sections, so that any group element sections all of sufficiently long values end up in that finite collection. Like maybe I can give you an example of a contracting one that actually once, I'll go back 1 second. For instance, this adding machine is contracting. The nucleus is exactly this automaton. If you start taking powers of this automaton, what you'll see, so I mean, this is generated by A. This is a cyclic group generated by A. And what you'll see is that the sizes of the sections of powers of A go down by roughly a half. And so eventually they'll get into either A or identity. So like if you look at the sections of A squared, you'll see one section is, let's see, I think if you do A squared, if I'm not mistaken, you'll get both sections are A and things like that. And so things start to decrease. Okay. Where was I? Scenic groups. All right, so let P be a prime and let F be a polynomial over the P element field of degree greater than 0. So it's not constant. And its constant term is 0. Is not 0, sorry. Is not 0. And let MF be the companion matrix of F. So because F of 0 is not 0, the companion matrix is invertible. That's why I chose F of 0 not to be 0. So everyone's happy with what I mean here, right? So you take some polynomial, we write down its companion matrix. This is sort of an indecomposable, in some sense, matrix. And GPF is going to be the following self-similar group. Let me see, am I able to write on the screen to try to draw a picture? Let's see, I think I can draw on the screen. I'm gonna try drawing on the screen. We're gonna see how this goes. Okay, so the alphabet you're acting on is just Z mod P. So I'm gonna draw this like P is equal to 3. Okay? Then we're gonna have a permutation sigma, which cyclically permutes the 3 trees hanging off. Okay, and it does nothing, it just cyclically permutes them rigidly. So it's going to move T0 to T1, T1 to T2, and T2 to T0, and not change anything else. So its sections are all trivial afterwards. All right, so you know, sigma on a word, you know, like 1W will be 2W. So is it clear what sigma does? It just cyclically permutes the first letter, and so it's clearly an automorphism of order P. Okay, I think I can now delete all that stuff that I did. Okay, and it's also going to be generated by a copy of Z mod P to the n, so a vector space of dimension n. Oh, let's see, which acts as follows. So elements of Z mod P to the n, they fix the first letter. And then they act on the other letters in the following way. So here I have some vector v, which is in Z mod P to the n. And here what I'm going to do is I'm going to take my companion matrix, apply it to v, and that's how it's going to act on this tree. This gives me a new element of zp to the n, and that's my section. On the second tree, I'm going to act as the identity. And maybe I should call this ID. And on the third one, what I'm going to do is act as sigma to the last component. So here v, or maybe it should be v2, sorry, because I'm doing indexing mod 3. I act as sigma to the last component. Sorry, I'm having trouble hitting the correct button, where my vector v looks like this.
But I'm sorry. I mean, if you multiply mf by times v, that gives
I get a new
vector. Yeah.
It gives me a vector which is an element of my group. So that's my section. That's what the cocycle does. So my vector v does not move the top trees. On the first tree, it's going to do whatever the vector mfv does. On the second tree, it does the identity. And on the third tree, it does the cyclic permutation, but the number of times it does it is whatever its last coordinate says to do. And so in particular, notice this guy does do something. It moves this tree around.
Mm-hmm.
And so this guy here will eventually move somebody, because eventually there's some subtree where it's going to do something like that. So that's kind of how it works. I know if you've never seen this kind of stuff, it's kind of hard to absorb these self-similar groups if you haven't seen them kind of in action. It's one thing. And this is a contracting group, and the nucleus are exactly the guys I wrote down. So one can show that. This requires a proof, but you can show that basically if you take long enough sections, you're always going to end up with either a power of sigma, maybe the identity power, or you're going to get somebody which is in this thing. For example, the famous Grigorchuk group is you take your prime to be 2, and you take the irreducible polynomial 1 plus x squared. And this guy has companion matrix that looks like this. That's the companion matrix for this one. The Grigorchuk-Oechsler group is x squared plus 1, so that's the companion matrix, which is a, oops, sorry, I mistyped that. That's supposed to be 0. It's supposed to be a transposition matrix. Okay, and the last one is a degree 1 polynomial, so the companion matrix is just 1. Not very interesting example. But this is another group which has a name. And Sunik gave necessary and sufficient conditions for these kinds of groups to be P groups of intermediate growth. So they're kind of generalizations of the Grigorchuk group. And so here's what we proved for these guys. If you take a Sunik group of where the polynomial has degree n, then if n is 1, the corresponding algebra is always simple over all fields. So this includes things like that Frabajowski group to group. If n is bigger than 1, then our matrix MF is a permutation, and it acts on the projective space over Z mod P to the n, right? So we just look at the lines. We look at the set of all lines in this vector space, and MF acts on it. And if it acts transitively on the set of lines, then the Nekrashevych algebra is simple, except over fields of characteristic P, where it's not simple. And if n is greater than 1 and this does not act transitively on projective space, then this algebra is never simple over any field. Okay, so for example, also, if you look at what Sunik proved, you see that when it acts transitively, this forces it to be a P group of intermediate growth. So that's a good example. So we look at the Grigorchuk-Oechsler group. Its companion matrix is this permutation matrix, which fixes 1, 1. And so it does not act transitively on the lines. You cannot move the line 1, 1. And this tells you that the algebra is never simple. On the other hand, if you look at the one for the Grigorchuk group, this is the matrix for the Grigorchuk group, and this cyclically permutes the 3 lines. This is actually essentially the matrix for the primitive element of F4. So it actually it cyclically permutes all the vectors. And so this one does act transitively, and so you get a simple group, a simple algebra, except for in characteristic 2, which was observed already by Enrique's group of people. But this kind of tells you what's going on, and you can see that you can kind of build examples to your favorite specifications once you know that this is the case. And again, this is the nice thing about our algorithm is even though our algorithm is an algorithm, if you understand what the algorithm would do, you can just figure out what the algorithm will say on these guys, even though it's an infinite family. So that's the nice thing. Of course, we ran the example first on the Grigorchuk group, and then once we understood what was going on, we proved that always happens. Okay, so now unfortunately I have to get into techniques because my time isn't up yet. When do I go to actually?
So you can, I mean, you can go say 50 minutes will be 5 minutes more. That will make your talk 50 minutes long. But
Okay, that's okay then. So I'll go a tiny bit longer, but I would probably try to avoid the last slide or two.
Okay, fine.
Because probably most people it's still the morning, although for some people maybe not. So suppose I have a self-similar group in Tx, then the Nekrashevych algebra is generated by the group G and these elements XX star. And I'm going to now make things into a star algebra by inverting starring words. And then you can write the defining relations as the multiplication for G. You have this funny thing that tells you how sections act. You have the star version of that. And you have this sort of cone kind of rule. And then you have the Kuntz-Krieger rule, CK2. And all these except for number 5 use just multiplication. So 1 through 4 define a contracted monoid algebra. So if you ignore contracted, just means that the 0 of the monoid and the 0 of the ring are viewed as the same. So the basis are the non-zero elements, and the product being 0 is really 0. Okay. And then the Nekrashevych algebra is this monoid algebra plus one extra relation, CK. And this monoid consists of all zeros and the elements of the form U, G, V star, where U and V are words and G is from our group. I mean, these rules here are basically a complete rewriting system or a diamond lemma thing, and you can just use these rules to rewrite everything in this form. You know, that's pretty much what this rule. This rule tells you how to move a G to the right of a letter, and this tells you how to move the G to the left of a starred letter. And this rule tells you how a starred letter followed by a non-starred letter is dealt with. And it's an example of an inverse monoid. So an inverse monoid is a monoid such that for every M and M, there's a unique guy M star with these two properties. So groups are inverse monoids, and inverse monoids are partial symmetry as groups are symmetry. So this guy MGX is an inverse monoid. And not only is it an inverse monoid, but it has the property that has no proper non-zero quotients. So in inverse semigroup world, we call this being congruence free. So it has no quotients other than the 0, no proper quotients other than the 0 monoid.
Is this non-zero quotient property obvious? Has it been proved by you, or?
I mean, it's not difficult, but I mean, so there are 3 things that you need for an inverse semigroup with 0 to have no quotients, and they're kind of similar to what you expect in groupoids. So you have to check that. You have to check something that has no, that you can't smash idempotents together, and you have to check that you have no ideals, no non-zero ideals, and then there's a condition on the idempotence which is satisfied here, called semi-disjunctive. So there's a simple criterion, and it's easy to check this guy has it. Mm-hmm. And this ideal, that's the CK relation, is special case of Exel's tight algebra of an inverse monoid algebra. And I proved with Laura, we proved in our previous paper that if you have a congruence-free inverse monoid, then it has a unique maximal ideal containing Exel's tight ideal, which we call the singular ideal. And we give a purely algebraic description of this ideal. It corresponds to the singular or essential ideal, but it has an algebraic description. And for this particular monoid, we can tell you exactly, well, it's the kernel of the action on the infinite words, but we have a very concrete description of it, which is what we use in the paper. So this is the characterization. So if you have an element of this monoid algebra, it belongs to this Kuntz-Krieger style ideal if and only if it annihilates all words. So there's an integer k, so that a times any word of length k in this monoid algebra is 0. And it's singular if for any word u, there's a way to make it longer so that it gets killed by a. So in particular, if it satisfies this condition, then it's obviously singular because a times any sufficiently long word is 0. But this is not saying any sufficiently long word. It's just saying there's some sufficiently long way to continue this and get to 0. And then there's a key reduction. We can show that this is simple if and only if there's an element of the group ring. which is not singular, sorry, which is singular, but not in this Kuhn-Krieger ideal. So you don't have to look at arbitrary elements of this monoid algebra to figure out whether the Kuhn-Krieger ideal is a singular ideal. You just have to look whether there's something in the group algebra.
So
and in the case that is contract, go ahead.
Yeah, this singular ideal is the one that measures Hausdorffness, right?
Well, if it's not Hausdorff, then the singular ideal is the same as the Kuhn-Krieger ideal. Yeah. But it can still be zero even when it's not Hausdorff. I mean, it can still be the same as the tight ideal when it's not Hausdorff. It possibly can. That's exactly when this algebra will be simple. And the other big reduction is that if it's contracting, you can show if there's any element which is singular but not in the Kuhn-Krieger ideal, then that element can be chosen to be in the group algebra and supported on the nucleus. So the whole game is looking at things supported on the nucleus, and that's a finite set. That's why we can get down to a finite algorithm. So if I take, so the nucleus is a certain finite automaton, and it turns out that the condition to be singular is given by a finite system of z-linear equations, and the condition to be in this ideal is given by a larger finite system of z-linear equations. And so it's easy to check if there's a solution to the smaller system, which is not a solution to the larger system. You're basically comparing ranks of coefficient matrices. And the ranks are going to be the same over Q as they are over all but finitely many primes, because you can put things in Smith normal form and look at which primes change the rank, and it's only going to be a finite list. And so the whole game is coming up with this system of equations, and then you're doing Smith normal form. And Smith normal form is fairly efficient. The problem is the number of these equations, how many there are, and is the complication to bound. Let's see, do I have any time to say anything about this? Or I guess I do, unfortunately. So here's the messy part of it. What we do is we define an action of the free monoid on the set of equivalence relations on the nucleus. So the nucleus is this finite set of automorphisms in your group, this finite subset of your group, which is closed under sections into which all things eventually get into. And we define an action of the free monoid on equivalence relations. I define it on a letter by saying that x times an equivalence relation, whatever, makes G and H equivalent if G and H, first of all, they permute x the same way, and secondly, their sections are equivalent for the original relation. So we're saying basically acting by x means that to be equivalent after you act by x means that your sections on x are equivalent, and you do the same thing with the letter x. So this is some sort of thing. And then we define for each word w the result of having w act on the equality relation. So the equality is an equivalence. So in other words, what this means basically is that G and W should, G and H should agree on W, and their sections at W should actually be literally equal, which is what it boils down to. And since N is finite, there are only finitely many equivalence relations of this type, and this is an X and star invariant set. So this is the place where we don't have a good bound, is how many of these equivalence relations actually show up. So, you know, the number of equivalence relations on a set, on a finite set, can be fairly big. So that's where but in practice, I've never seen the subset of equivalence relations be all that big. So the question is really what percentage of equivalence relations really can come up this way. I suspect there's a better bound than just saying that it's finite, than just the number of equivalence relations. In any event, what we do is we have this finite set, the free monoid acts on it, so we can build sort of a Schreier digraph or an automaton for this action, and we can compute it effectively. And we look at what are called essential vertices. These are vertices which can be reached from a cycle, and minimal vertices, which are vertices that you cannot exit from its strong components. And then roughly speaking, so particular minimal vertices are essential. And roughly speaking, given any equivalence relation, on n, we get an equivalence. We get some equations by saying that we choose a variable for each element of the nucleus, and we say that the sum of all equivalent guys should be equal to 0. So for each equivalence class, we say the sum of the guys in that equivalence class should be 0. Another way to say this is we want to look at those elements which go to 0 when you factor out by this equivalence relation. And the key point is that basically you satisfy these equations means that when I multiply by the word, if you satisfy the equations for word w, means when you multiply by w, you get 0. And the main theorem about this stuff, again, is technical, so I'm not going to say you're going to get it necessarily, is that A belongs to the Krieger ideal if and only if it satisfies the equations associated to essential vertices. And it belongs to a singular ideal if and only if it satisfies the equations corresponding to minimal vertices. So there's a finite set of minimal vertices, a finite set of essential vertices. The minimal vertices are essential, and we want to know whether these equations have a solution which is not a solution to those equations. So are these equations implied? So in other words, whether these equations are implied by those equations. And so that you can do. And in practice, somehow these don't get too big. In many examples, in a lot of examples, all the vertices are essential, and most of them are minimal, and things like that. We only have a couple of examples where there are even non-essential vertices. So that's how it goes. And I had some closing remarks. I don't know whether any of them are interesting. Anyway, I think I'll just go to thank you for your attention.
Thank you very much, Ben, for your talk. Very, very, very impressive results. So are there any questions from the audience? See? Well, I have a question that I think, I mean, it's a variation of a question I already asked you, both of us, I think.
Okay, so yeah, the different answers this time.
Because I asked everybody. So do you have any idea of coherence for these algebras you consider? Coherence.
Coherence.
Yeah.
For Nekrashevych algebras or arbitrary groupoid algebras?
No, for these algebras. The Nekrashevych ones, even if you want the simple ones among them. For some of them, do you know that they are coherent? So the Levitt-Pass algebra
So you want every right ideal to every finitely generated right ideal to be finitely presented? Is that?
Yeah, yeah.
Okay, so my feeling is that it probably won't be. I didn't think about this very hard, but for instance, well, okay, so I guess the first example question, I see. So in the Levitt case, it is coherent, right? Because it's hereditary.
Mm-hmm. Yeah.
So okay, so that's a good sign there. Let me think. Okay. Now these guys are not, I think, in general going to be hereditary. I haven't thought about coherence of them. That's a good question. For these cases, maybe there's a better chance because in some sense they're very close to like, you know, the Levitt style algebra, but of course the group could mess up coherence. Although, I mean, you know, the group algebra does not have to embed, but I guess there probably are examples where the group algebra does embed. And so maybe you want to at least ask the group algebra to be coherent or something, which is not, say, unreasonable. I mean, that may not be necessary, but it may be helpful. You know, like if the group algebra is free or one relator or something like that, of the group. I mean, I think you would want some conditions on the group, but I haven't really thought about coherence. I don't have a good sense on proving rings are coherent.
Okay, another question is in general for self-similar groups, when you construct this group. You construct a groupoid out of them and take the groupoid algebra. And in this groupoid, the isotropy, I think they're called isotropy groups, the ones that fix each.
Yeah.
So do they, I mean, what's the relation between them and the group? Are they subgroups of the group? Are they? You just froze on me. I don't know if it's me. Is people here? Are you people hearing me?
Thing like that. That's the kind of things that typically come up, if I'm not mistaken. Maybe
You are freezing. So I didn't hear you or the
the
recording.
periodic word. I think you may get some
7
extra Z stuff.
minutes.
I think it depends on, you can consider the elements that are, say, how to say that? The elements of the group that fits any letter in your alphabet, and then you can, say, describe a direct limit of the stabilizers. And then whenever you perform this direct limit, what you get is the isotropy group of any infinite word that corresponds to the points in your your unit space. So somehow, if
But
you
don't you have
can,
to factor out by the things which strongly fix that infinite word? Then you take the things which fix the infinite word, and then you factor out those which strongly fix. Because if it strongly fixes, then the term becomes trivial.
well, yeah, most likely, but you should be careful. I'm speaking very roughly, but at some point, I think, at least for the Excel part algebras or for self-similar graphs, I think we did with Ruiz some computations in the direction, but the problem is that then you need to keep track exactly of which is the restriction. So the one cocycle, the group, and the stuff. So it's quite involved. But you can say theoretically compute the isotropic group at this at any infinite paths if the graph is finite and has no source of things. But at the end, you cannot get really right of which is the concrete group you get in each point.
I mean,
Most of them, yeah.
no, it is easy. I mean, you take a word, or if you want in your setting, a path, a finite path,
Yeah.
and a group element, and you can easily build an infinite path that is fixed by the group element. But yeah, but then you don't know who else fixes that element.
Well, I think also the complicated bit is that the group elements, they can have the trivial germs. Non-trivial elements can have trivial germs. If you have that it fixes a prefix of an element, and then it's section that element is trivial, then that will represent the identity element in the groupoid of germs. So that corresponds to sort of fixing a neighborhood of that element. So my general impression is typically, if you're working in the case of self-similar groups, which is a bit simpler because vertices don't move around, is that essentially what you get is those things which fix the infinite word modulo those things which fix a neighborhood of the infinite word. But if you have an ultimately periodic word, there might be some other stuff that comes in because of the ability to the Z stuff coming from the left. The vertice 2 or something as well. I remember I only recently played with the self-similar graphs, and if you don't fix all the vertices, it's more complicated. But I think somehow the crucial issue has to do with first of all, you want to avoid the ultimately periodic behavior because that just adds some extra z type information, and then it boils down to stabilizing the infinite path, but not stabilizing any neighborhood. Or two guys which stabilize the infinite path but agree on some neighborhood will become the same.
Yeah.
Because this is a strongly fixing property which appears all over the Excel part of the paper. At least that's my understanding. I could be wrong though. But in particular, it's not so easy to say, oh, my group is torsion free or all my isotropy groups torsion free. Because there is this quotient that comes up from quotienting out the things which fix a neighborhood. And that makes it a little bit more complicated.
So, okay, so the group, then, I mean, so the group comes with this presentation, which is acting on this tree, and the groupoid you construct, you don't have quite a good grasp on the stabilizers that you get in the groupoid, but perhaps one can find another space where you can control the stabilizers. But it's not the tree from which the group, I mean, that you use to define the group.
I mean, for the stabilizers on the tree, it's not so difficult. It's for the boundary of the tree. But if you don't go to the boundary of tree, you're not going to get the right algebra.
No, of course. Yeah. That's what I meant. I mean, in the groupoid, you necessarily, I mean, you can include the finite words or not, but you must definitely include the boundary, the infinite words.
Yeah, and then under fairly mild conditions, there's stuff on Nekrashevych. I believe that there are essentially generic kind of stabilizers. So I think that that you'll find that certain stabilizers are what you kind of typically see, if I remember correctly. At least stabilizers of infinite paths, and then I'm not sure what happens when you try to go to the corresponding isotropy part of the groupoid. But yeah, so it's not, you have to look at your example, and then in your example, you might be able to figure out what the isotropy groups look like. Particularly for contracting groups, all the isotropy is going to be determined by basically things happening with the nucleus, if I'm not mistaken. And so you can get better control, I think, in the contracting case, because looking at the nucleus, that's how you act far enough down. So in some sense, by just absorbing in a very long prefix of your infinite word, eventually what happens is going to be the nucleus, and either that nucleus is going to strongly fix that word or not. So I think the nucleus kind of controls what's going on. And so for I believe, for instance, for these like cynic type groups, all the stabilizers, even when it's not a P group, all the stabilizers are still finite except for the ones that ultimately periodic words where you can throw in some of the Z action. If I'm not mistaken.
Okay.
Although I didn't write that out rigorously, I convinced myself that should be true.
All right. So are there any more questions or comments from the audience? So if not, then I will stop the recording now.